Okay, these are the topics today. The first topic, spline interpolation. I want to show you two examples. The second topic, basic splines. In short, we call basic splines, B-splines. Take a review about what is spline interpolation. Given a table of some values of function f, we call x, we call these points nodes, and the points t0, t1, tn, we call them lines, different. The logs and the lines may or may not be identical. Now we have a table of some function values. We want to pick a function s from this space such that this function s interpolates the table. In other words, satisfy these conditions. Yeah. This problem, how to choose s, this problem is called spline interpolation. Review number 2. In the last class, we learned that these functions in how many functions? N plus k. These n plus k functions, they form a basis for this space. Now we have a basis in hand. Spline interpolation becomes easy. It is an easy job. Okay. Okay. Let me show you two examples. This is a topic 1. Topic number 1, spline interpolation. Take a look at two examples. Actually, one example, but has two parts. Given the lines four lines, T0, T1, T2, T3, 4 lines. So in this case, n is equal to 3. N is equal to 3. Yeah. Yeah. This n is 3. T0 is 1. T1 is 2. T3 is T2 is 3, 4. Okay. Given the lines, this example has two parts. Part 1, A, find a function s from this space. S n now is 3. N is 3. K S is a piecewise polynomial function. The polynomial, the degree is 5. Yeah, 5. From this space, find a function. The function interpolates this table. This table. Yeah. Y is some function. F1, 2, 3, 4. Function value is -1, 3, 0, 2. Okay. Now in part A, in this part, the logs and the lots identical. In part B, the logs and these lots different. Then let me solve part A first. Solution. How to find a piecewise polynomial of degree 5 so that the polynomial interpolates this table. Yeah. Now we have a basis in hand. This job is easy job. Okay. Why? How? Okay. About this space, a basis of this space is okay. Go back here. N is 3, K is 5. So this is a basis. It is 1 x squared x3 x4 x5 and then x minus t1. T1 is 2. Power is 5. Then truncate is power function. Then x minus t2, right? Minus t2. Yeah, x minus t2, then x minus t n minus 1. T2 is 3. Power is 5. Truncate is power function. So how many functions? 8 functions. N plus k. N is 3. K is 5. So 8 functions. Yeah. This set of functions is a basis for this space. Now, any function in this space is a linear combination of these 8 functions. I let S from 3, 5, this space interpolates the given table. Okay. Express S as a linear combination of the basis functions. Okay. Okay. Now I express A0. What is A0? Will be determined times 1. A1 times x. A2 times x squared. A3 x to the third. A4 x4. A5 x5, right? Linear combination of these functions, and then plus some number times this function plus some number times this function. So, and then plus B1 x minus 2, B2 x minus 3, 5. Okay. Now, let me determine the coefficients from because the function S interpolate the table. From the table, I can obtain some equations to determine the coefficients. Okay, since I assume S interpolate the given table, so S the value of S at 1 is regular 1, right? At 1, value is negative 1. At 2, 3. At 3, 0. At 4, it is 2. 3. S at 3 is 0. S at 4 is 2. Now, these conditions lead to the following equations. Then we have plugging 1 in X. Again, A0, A1, A2, A3, A4, A5. Plugging 1 in X. By the definition of a truncated power function, because of 1 less than 2, by definition, this is a 0. 1 less than 3, this truncated function is 0. So from this equation, we have this equation. This is equal to level 1. Now, plugging 2 in X, then I get A0 2 times A1, then 2 square A2, 2 to the third A3, 4 A4, 2 to the fifth A5. How about here? 2 less than or equal to 2, still 0. 2 less than 3, 0. So this condition gives this equation, number 3, second equation. Okay, now plugging 3. Yeah, from here, plugging 3 in X, then I get A0, 3 A1, 3 square A2, 3 to the third, 3 to the fourth, 3 to the fifth, A5. Now this time, because 3 greater than 2, truncated power function is the normal power function. So 3 minus 2 to the fifth. So this is a plus B1. And then 3 less than or equal to the number 3. So actually this is 0. So I get 0, this equation. Now, the last condition, plug in 4 in X. 2, 3, 4, 4, A4, 4, 5, A5. And then let me see. 4 greater than 2. So truncated power function is normal power. 4 minus 2 to the fifth. So 2 to the fifth, B1. And then plus the number 4 greater than 3. This becomes normal power. 4 minus 3 is 1. 1 to the fifth is 1. So plus B2. And it's equal to 2. 2. Yeah, 2. Yeah. So this linear system determines the coefficients. 4 equations, but we have 8 unknowns. So the linear system has infinitely many solutions. Let me write the linear system in equation, matrix equation. Okay, in matrix equation, the linear system is this: 1, 1, 1, 6, right? Yeah, 6, 1. Then 0, 0. 1, 2, 2 square. 2 to the third. 2, 4, 2, 5. Then 0, 0. 1, 3. 3 square, 3 to the third. This is a 1, 0. And then 1, 4. 4 square. 2 to the 5th, then 1. And then times the unknowns. A0, A1, A2, 3, 4, 5. No. 5, yes. Then B1, B2. And the right hand side is this linear system is underdetermined linear system. It has infinitely many solutions. One solution is this. One solution is this. Yeah. One solution. One solution is negative 5, A0, A1, A2, A3, A4, A5, negative 7, 2, 1, 5. Yeah. And the corresponding spline function is plug in this solution here. Then the corresponding spline function is this. So when we have a basis of the space, interpolation becomes very easy. A second solution. Second solution is negative 5, 3.6, 1, 3.5, negative 3.1, negative 4, 1, 4, 3. And the corresponding spline function is this. Minus this basis is simple. But the drawback is the functions in this basis is power function. This is a drawback. Why it is a drawback? Because when there are powers, when x is large, greater than 1, then the power make the function values increasing exponentially. When x less than 1, decreasing exponentially. So the magnitude of function values in this spaces in different orders. When this line is, say, xk is huge, when you compute spline function through these spaces, your computer consider, the small powers, say, consider 1, 0. That is a problem. So actually, from this matrix form of the linear system, we can see that, you see, there are powers here, powers, right? Powers. Where 5 is k, the degree of polynomials. When k is large, these powers go up exponentially. So when you solve this linear system, your computer consider the small numbers. Say the first column, say the numbers about here, right? About here. Your computer consider them all zeros. As a result, the solution is not accurate. So this linear system actually is a linear system of random mark. Like, not exactly. Yeah, this matrix is not exactly a random matrix, but a random like matrix, the coefficient. So the entries in this matrix, they are not in the same order in magnitude. Okay. Some entries are very huge, and some are very, very small. So when you solve this linear system, computer consider small numbers or zeros. So this linear system is numerically, we call this linear system a U condition linear system. U condition. U condition linear system. Linear system. Yeah. U condition linear system. That means that highly sensitive to round-off error. Okay. So this is a drawback about the basis. Okay. This is part A. In part A, the logs and the logs, they are identical. Now in part B, the logs and the logs different. Part B. Given this table, uh, 1.2, 1.7, 2.5, 3.1, 3.5. Function values are 1, 0, -1, 0.5. How many logs? Okay, in total, 5 logs. 5 logs. Okay. Okay, now the question, same question. Find spline function from S3, 5 from this space. Such that S, the value of S at 1.2 is equal to 1. Yeah. S at 1.7 is 0. S 2.5 is equal to 1. S 3.1 is 0. Such that S, this function, interpolates the given table. Okay, now the solution is similar, expressed as a linear combination of the basis functions. Of the basis functions, yeah. A0, A1, A2, A3, A4, A5, then plus B1, 5, B2, 5. Okay, now plug in the data in S here. Okay, then these 5 conditions lead to the following linear system: A0, 1.2, A1, 1.2 square, A2, 1.2, 3, A3, 1.24, A4. It is 1. Then 1.7. A5, 0, 1, and so on. Okay, yeah. Let me skip the details. The details is in my notes. So 5 conditions lead to 5 equations. 5 equations. 5 equations. How many unknowns? 8 unknowns. 8 unknowns. Unknowns. A0, A1 to A5 unknowns. Then B1, B2 unknowns. So in total, 8 unknowns. So this linear system has infinitely many solutions. One solution is this. Okay. A0, 12.63. A1, 11.8x. A2, -1. A3, 2. A4, 0.7. A5, -0.38 x5. And then B1, 10.71. 5. Yeah. So in part B, the loads and the lines different, but still we can still define spline interpolation. The problem is well defined, still well defined. Okay, so yeah, this is one example about spline interpolation. Okay, as I just mentioned, this basis leads to a random like linear system, very new condition. Usually, when you solve the linear condition, when k, especially when the power is large, 100, say for example, usually you cannot get any accurate solution. So in the second topic, we give up this basis and try to find a second basis. The second basis doesn't involve any power, okay? any power. So the second basis is used currently in practice. Topic 2. Okay, topic 2. Yeah. Basic splines. In short, B-splines. B stands for basic. I combine these two sections together. This is a topic 2. Topic 2. Yeah, we want to develop a new basis. A new basis for S and K for this space, and give up, okay, the power basis. There are 2 steps to construct this new basis. Step one, 2 steps to construct this new basis. Step 1, we first construct a system of certain basic spline functions. Yeah, basic spline functions. Briefly, we call them B-splines. Okay. First, we construct B-splines. Step 1. Then step 2. Construct a new basis for S and K from the B-splines. 2 steps. Okay, now step one. Okay, now step 1. I want to define some basic spline functions. Okay. First, specify a sequence, infinite sequence. Actually, not okay. An infinite sequence of nuts. Of course, these nuts on the real line, okay, on the real line on x-axis, okay. T0 less than, yeah, of course, this nuts is in increasing order. T0, T1, T2, Tn, yeah. This n+1 nodes we often use. Now I extend these n+1s to infinity on the right side and also on the left side. So the next line is a Tn+1, Tn+2, and so on. Extend it to infinity, okay? And on the left side, T-1, T-2, T-3, and so on. And so on. Okay, now B-splines, basic splines, will be defined or constructed constructed based on this infinite sequence. Okay. Let me before I continue, let me make a remark. Okay. The spline functions. The spline functions in S and K are defined on some interval AB that contains this n plus one lot T0, T1, T2, and Tn. Yeah. As we saw from the definition of this space in previous classes. But now, basic splines. But the B splines are defined on negative infinity to positive infinity. Okay, yeah, we use all the lines in this sequence to construct B-spline functions. So B-spline functions defined on the whole real line, right? The whole real line. Okay, now let me after this remark, okay, let me define B-splines. Number one, basic splines of degree 0. That means that over each subinterval, the degree polynomial degree 0. Degree 0 means a constant over each subinterval. The B-spline constant. Okay. Okay. Notation. Notation is rotation. B. Basic. Okay. Basic spline. Degree is 0. K is 0. K is the degree of polynomials. And then I, this I related to some subinterval. Okay. Yeah, the notation is this. Okay. Now definition is this here. P I 0, it is a function, depends on x. And when x is in this interval, Ti plus 1 over this interval. Okay, now this is the x-axis. What is I? I can be any integer, say negative 100, negative 8, 0, positive 8, positive 99. Okay, yeah, any integer. Okay, say here is a Ti plus 1. Over this interval, this spline function is 1. Value is 1. And outside this interval, the value is 0. Yeah. So the graph is, yeah, here. Solid point. All right, because this is a close on the left. Then open. Yeah. Horizontal. Yeah, the height is 1. Then here is 0. is 0. Okay, then open, then solid 0. Right? Yeah, this is the graph of this function. Okay, where I any integer, okay, from negative infinity to -2, -1, 0, 1, 2, and then go to infinity. Yeah. Yeah. Okay, this is a spline function of degree 0. It is the starting point to construct a B-splines. Yeah. Okay. Before I present a formula for spline function of degree 1, spline function of degree 2, let me give you some properties about BI0. Okay, BI0. Some properties. It is easy to see these properties. Some properties about B-splines of degree 0. Very easy to see that. Okay. First, B-spline of degree 0, non-negative, right? Everywhere, non-negative. For all integer I and all x non-negative. BI0 is a continuous function, not from the left, but from the right. Is continuous from the right-hand side on the entire real line. Right? Easy to see this from the graph of this function, right? C, the support, a terminology from functional analysis, the support of a function. The support of BI0, this function, what it means, the support. The set of x where the function is non-zero. Yeah. The x values, the set of x values where function is non-zero. The set is called the support of the function. The support of this function from the diagram clearly is the interval. Yeah, including ti, but not including ti minus 1. Yeah, only over this interval, this guy non-zero, and is 0 in other any x value. D, poverty D, okay. Summation BI0 at any x I from negative infinity to positive infinity is equal to 1. Yeah. For any fixed x. How to see this equation? How to see this equation? Yeah. Okay. Proof. Okay. Okay. Say x. X is a point on the real line, but the real line now is covered by subintervals. So x, assume X is in, X must be in one and only one subinterval. Say is in this interval, T K minus 1. Okay, suppose. Okay, then this I don't have space. Okay, how about let me write my proof on the next page. Then summation I from negative infinity to infinity bi 0 x is equal to, it is a infinite sum. Okay. Okay. When I is k here, then I is k plus 1, k plus 2, 0, and so on. Infinite sum. Okay. Then this is a bk minus 1 x 0, and so on. Infinite sum. Infinite sum. But because x must be in some, in one and only one subinterval. Yeah, I assume it is in this subinterval. Okay. So by definition of this function, all the terms are 0 except this term. This term is 1. And then plus, yeah, this 0 plus 0, and so on. So yes, this is a infinite sum, but essentially it is a finite sum. Okay, the finite sum actually is equal to 1. Yeah, this is equal to 1. So for any x, for any x, when you sum up these B-spline functions, the sum is 1. Is 1. Okay. Yeah. Okay. Today, I first define spline function of degree 0. Then next time, starting from this definition, I recursively define spline functions, B-splines of degree 1, degree 2, and so on, and so on. Yeah, let me stop here.